Good morning. Today we will discuss multivariate analysis of variance. Multivariate analysis of variance, which is popularly known as MANOVA. Today's contents are conceptual model for MANOVA, assumptions for MANOVA modeling, estimation of parameters, model adequacy tests, interpretation of results and references. We will see that how much is possible to complete today, and the remaining portion we will be completing in the next class. You see this slide. Last class I have shown you that when L equal to 2, where L stands for number of population and P is 1, then we have used t test, that is the difference between two population mean, that is described through as H0 mu 1 equal to mu 2 and H1 mu 1 not equal to mu 2. And for the p greater than equal to 2 case, that is multivariate case, here also this H0 mu 1 equal to mu 2 and mu 1 not equal to mu 2, but this mu 1 and mu 2 are in the vector domain when p equal to 2, that is the 2 cross 1 vector, and we have used Hotelling t square. Last class I have told you that when L greater than equal to 2, that is 3 or more, for one variable case you will be using ANOVA, and we have discussed one way ANOVA, two way ANOVA, three way ANOVA and multi-way ANOVA concept. Now, if your number of population is more than 2, that is 3 or more, and as well as number of variables are more than the 2 or more, in that case what will happen? You will find out that you require to use MANOVA, not ANOVA. So, essentially what we have discussed then, when we will go for ANOVA, ANOVA is you have L number of population, L can be 1 to capital L, that is 1, 2, 3 like this is the L 1, 2, 3, and you will collect ith number of I equal to 1 to dot n number of observations, and you are interested to see the difference in population means, where population is determined by L1, L2 like 1 to L, that is the case. Everywhere the mean value you will find out, here the mean value you will find out mean 1, we can say x1 bar, x2 bar like this, then finally x bar, that what we have seen last class. Now, in case of ANOVA, that L is greater than equal to 3, that means what you mean to say that if there is 3 or more population with one variable p equal to 1, you are going for ANOVA, and when p L greater than equal to 3, but p is 2 or more, then you will go for MANOVA. And your hypothesis what you will propose we will see later on, but before that let us see one example. This is an example. Last class in ANOVA we have seen that process A, process B, process C producing steel washers with certain quality characteristics, that is outer diameter. So, with one quality variables. Now, here we are adding one more quality variable, that is inner diameter. So, that means the steel washers produced by the three processes are measured in terms of their two quality characteristics, that is outer diameter and inner diameter. So, here P equal to 2, and there are three processes, process A, process B and process C. So, our case example case is capital L equal to 3 and small p equal to 2. So, this is a case for MANOVA. This is a case for MANOVA what we have discussed here. Okay. I told you in last class also the one of the useful way of looking into data is the box plot, and if you see the box plot for the two different variables inner and outer diameter for the three different processes, process A, process B, process C. You have seen in last class that for outer diameter the mean differences are quite visible from the box plot, and if you see the lower figure where it is the inner diameters are plotted in terms of box and whiskers. So, you find out the mean value for process A, that means the mean inner diameter is this one, mean inner diameter for process B is this, mean inner diameter for process C is this one. So, apparently if we want to say about the differences in means between the three processes, perhaps process A and B means are not different, but process C is different from process A and B. If you see the outer diameter case, here process A and C's mean differences are all not significant maybe, but process B it is different from both A and C. So, there are two types of pictures now. From outer diameter point of view, you are saying that, and also we have seen in ANOVA that process B is different than process A and C, but here if we add inner diameter, what is happening here, that process C perhaps will differ in terms of their mean values of inner diameter from A and B. Now, we want to see collectively what is the difference in mean vector, where this vector will be determined by mean diameter for outer diameter as well for mean inner diameter. Okay. So, collectively are the three processes different or not, that is what we will be testing through MANOVA. So, we require certain notations to fully understand the application of ANOVA as well as MANOVA, because in case of MANOVA there is one more more dimension is added as number of variables will be more than equal to 2. So, P will be greater than equal to 2. So, as a result you see in ANOVA what we have said, we said like this, that ANOVA case here it is number of populations, this axis and this axis is observations, and for different population you have obtained certain observations, and somewhere there is one observation which is XIL, ith observation on the lth population, and it is a scalar quantity. Now, in case of MANOVA what will happen, you will find out that one this side is number of observation, let it be population in the same manner populations, and this side is observation, that is number of observations. Then we will add one more dimension which is number of variables. So, if we denote number of population in terms of L, number of observation in terms of I, and number of variables in terms of J, then what will happen, your general structure will be like this. This is the data structure basically. Getting me? What will happen for any observation? Suppose if I say this is my XIL, getting me? This is our XIL, then XIL is no longer a scalar quantity. In ANOVA this is a scalar quantity, in MANOVA it is not a scalar quantity, because for this cell you see if I go 1, 2, 3 depending on the number of variables, this XIL will have more number of values. So, we can say here that XIL is no longer a scalar quantity, it is a vector. What we will write here? XIL1, XIL2. So, like this XIL, how many variables are there? P variables are there, P cross 1. And there is the complexity, because one more dimension is added and your total work is now in 3 dimensional case. It is not a 2 dimensional issue. If this is the case, so this is the general observation. Okay. This is my general observation. As you have p variables, so you also have p mean values. So, now I am writing that the mean vector for population L, there will be p mean values mu L1, mu L2, like this mu LP, p cross 1. And as there are p variables again, there will be one covariance matrix. If I write like this SL sigma L instead of S, we will be writing when we take the sample. Now, we are writing like this. Then what will happen? This will also be P cross P matrix, P variables are there. Your L varies from 1 to capital L. So, then there will be sigma 1, sigma 2, like this sigma capital L. So, there will be similarly mu 1, mu 2, mu capital L. For mathematical simplicity, we will be using this term, although this is a vector, basically we will be using this term like this XIL without bringing the variable part. Variable part is implicit here, because XIL is nothing but this one. This is the general observation. Okay. So, you see this is pictorially given in this figure. I think it is very clear now for all of you that ANOVA, where we have different populations and different observations, and for MANOVA it is not population, observation and variables, and this general observation is XIL, which is this one. Okay, you have to keep in mind this vector part. Then MANOVA assumes something, and MANOVA do also hypothesis testing like your ANOVA. What are the hypotheses here? What are the hypotheses in ANOVA? You said mu 1 equal to mu 2 equal to mu L, that is your H0, and your H1 is mu L not equal to mu M for at least one pair of mu L mu. One pair of mu means either mu L or mu M. L equal to 1 to capital L, M equal to 1 to capital L, and L not equal to M. And in MANOVA case, the same hypothesis is same, that we are saying H0 mu 1 equal to mu 2 equal to mu L. Please keep in mind, by saying this we are saying like this mu 1 1, mu 1 2, like this mu 1 p equal to mu 2 1 mu 2 2 mu 2 p equal to finally mu capital L 1 capital L 2 capital L p. That is the difference. In ANOVA case it is scalar quantity, MANOVA case it is the vector quantity. And your alternate hypothesis that mu L not equal to mu m. By saying this, you are saying that mu L 1, mu L 2, mu L p this not equal to mu m 1, mu m 2 for at least one pair of LM. Okay. So, like ANOVA, we will also partition the general observation. So, what is my general observation here? My general observation here is XIL. Let us see in ANOVA case, parallelly see MANOVA case. In ANOVA case, XIL is partitioned like this: mu plus mu L minus mu plus XIL minus mu L. This is the way you partition, and we say this equal to mu plus tau L plus epsilon I L. Mu is grand mean, tau L is the population effect, and we are saying that no model is perfect, it cannot predict exactly same exact value for all the observations, there will be random errors. So, sigma epsilon I L is the random error part. Okay. So, same partitioning possible in MANOVA. What we will write? X I L equal to mu plus mu L minus mu plus X I L minus mu L. So, it is similar, it is like this. We have seen that X I L is X I L 1, X I L 2, X I L p, p variables are there, which is equal to mu 1, mu 2, like our case is mu L, that is the grand mean case, plus if we write like this, I think earlier we have written mu L 1 minus mu 1 mu L 2 minus mu 2, the same manner you come mu, I think L, this is mu 1, now mu L minus mu. So, all cases L will be there, and then every case what we are doing, this is mu 1, this is mu p, not mu L, this is mu p, please write down this one as mu p. So, then mu L p minus mu p, that is why the problem comes, I have written m L, then plus same thing XIL, all this you write XIL 1 minus mu L 1, XIL 2 minus mu L 2, same manner you come XIL p minus mu L p. This is what is partitioning the general observation into 3 components. One is this one is the general observation, the left hand side, general observation vector, and right hand side this is your grand mean vector. Then other one, that mu L1 minus mu 1, this one we are saying population effect vector, and last one is random error vector. Okay. So, this partitioning, for this one, this partitioning we can write also in the same manner. Earlier we have written that this first one, this is XIL, fine, then second one is mu, that is also fine, then third one is it will be tau L. Okay, plus epsilon I L. So, this is my general observation, this is my grand mean vector, this is the population effect vector, this is the random error effect. Okay. So, if this is just, we will just explain what I mean to say, that let us write down the tau L case. This will be a vector tau L1, tau L2, like this tau LP, P cross 1 vector. So, when we say population, Lth population effect, that is related to all the variables considered. Here we are considering p variables. So, tau L for p variables. Okay. So, if we frame our hypothesis like this, that H0 mu 1 equal to mu 2 equal to mu L, and H1 mu L not equal to mu M for one pair of LM, then using this tau L concept, you can find out the null hypothesis also. What will be the null hypothesis? What is tau L? Tau L is mu L minus mu. Now, if H0 is true, if this one is true, that means all means are equal, then what will be the grand mean? Grand mean will be n1 mu 1 plus n2 mu 2 plus dot 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 n L mu L divided by n1 plus n2 plus n L. If all means are equal, then what will happen? We can write all mu 1 equal to mu 2 equal to mu L. So, it will be n 1 plus n 2 dot 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 plus n L by n 1 plus n 2 plus n L into mu, because this will be cancelled out. So, what do we mean then? We want to say that every mu will be equal to the grand mu. Getting me? So, then what we can say, that mu L equal to mu if H0 is true, which indicates tau L equal to mu L minus mu equal to 0. That means, we can create null hypothesis like this: tau L equal to 0, L equal to 1 to capital L, and your alternate hypothesis will be tau L not equal to 0 for at least 1 L. So, if you test this hypothesis in terms of mu and the other hypothesis in terms of tau L, you are actually doing the same thing. Okay. So, in MANOVA we will do this in the same manner like ANOVA, partitioning the, now we partitioned the observation. Now, we will see that how to partition the this one your variability part. But what are the parameters you are estimating in MANOVA? Your parameters will be this tau L, actually mu L also you have to estimate, mu you have to estimate, and you have to estimate also the error terms. And another issue here is, if you go for unequal sample size, then the weighted effect of the population, that sum will become 0, and if you go for equal size, that is again the sum of the effects of the populations will become 0. I think you can prove the second one also. We can, what about first one, why it is 0? What I mean to say, we are saying that sum total of NL tau L, L equal to 1 to capital L, this is 0. You see what is tau L? Tau L is mu L minus mu. So, if you write down here sum total of L equal to 1 to capital L N L into mu L minus mu, the LH, that is the left hand side, what you will get here? This one L equal to 1 to capital L N L and mu L minus L equal to 1 to capital L into mu. So, you have already seen that mu equal to n 1 mu 1 plus n 2 mu 2 plus n L mu L by this. So, that means that sum of this n L mu L can be written like this, can be written as this one can be written like this, this into this. Okay. And then that will be cancelled out, and you will become, it will be N L, here it is N L is there, you have not written this one is there. Okay. So, how it is okay. So, what we mean to say that this quantity is N 1 plus N 2 plus N L into mu, yes or no? And I have told you this, that N 1 plus N 2 plus N L mu equal to N 1 mu 1 plus N 2 mu 2 plus N L mu L. So, again this N 1 mu 1 plus N 2 mu 2 plus N L mu L is this one, N 1 mu 1 plus N 2 mu 2, this is this part, minus N 1 plus N 2 plus N L mu, this quantity equal to this quantity, becomes 0. Problem? You have to understand that the grand mean is mean of the means, weighted case here, N 1 mu 1 plus N 2 mu 2 plus N L mu L by total frequency, and this one is mu. So, you can write from here N 1 mu 1 plus N 2 mu 2 plus N L mu L equal to N1 plus N2 plus NL into mu. Then if you make minus, this will become 0. This is the case. Okay. Now we will see the assumptions. What are the assumptions? Population covariances are equal. Errors are normally distributed, errors are IID. We will see first population covariances are equal, how to test it. We will be using box M test. Here we will create hypothesis H0 that population covariances are equal. Okay. And your alternative hypothesis will be sigma L not equal to sigma M for at least one pair of LM. Okay. Now we create one statistic. So this is our hypothesis. Then create the statistic. Our statistic we are creating, suppose D equal to 1 minus U into M. So you require to know what is M and what is your U, correct. Now let us see the slide where I have written these things. In slide you see that M is minus 2 log L equal to 1 to L, capital L, that is the multiplication into that determinant of SL by S pooled to the power NL minus 1 by 2. This is what is actually the this ratio SL by S pooled. All of you know S pooled. What is S pooled? How to compute S pooled? Your N1 minus 1 S1 plus N2 minus 1 S2 plus NL minus 1 SL divided by what? N1 plus N2 plus NL minus, correct. So that you have seen earlier also in two variable two population univariate case, you have seen that N1 minus 1 into S1 plus N2 minus 1 into by N1 plus N2 minus 2, just check. So it will this is the case. Now again you see the formula. If your sigma 1 equal to sigma 2 equal to sigma L, then your S pooled will be equal to S1 or SL in general term. So that means this determinant by this determinant, that will be ratio will be 1. And why we have taken log? The log is taken to make it linear, because it is a multiplicative one. To make it a linear one, the log is taken here like this. So if when you have taken minus 2 log, it is coming like this. This quantity is linearized like this, summation of L NL minus 1 log S pooled minus L NL minus 1 log SL. This is our M value. Okay. So this M value, and what is the U value? U is summation of L equal to 1 to capital L 1 by NL minus 1 minus 1 by that is this sum into 2 p square plus 3 p minus 1 by 6 into p plus 1 into L minus 1. Okay. This is the development by box. So, now if you then you put m and u in D. Now, D follows chi-square distribution with new degrees of freedom, where nu is 1 by 2 p into p plus 1 into L minus 1. Okay. So, you have to remember this. What is your nu value? Nu equal to half p into p plus 1 into L minus 1, that is the degrees of freedom. For D. So, if your D greater than equal to chi-square alpha and nu, then you reject H0, that in population variances are not equal. We have calculated this for this data set. Are you not comfortable now to compute the covariance matrix for a given data set? For process A, the covariance matrix is S1, for process B it is S2, for process C it is S3. You will be using, can you recall the covariance matrix formula? What you have used? If your x is n cross p and your x bar is p cross 1, you have created x minus x bar, you also multiplied by 1. So, to make it n cross 1, I think you have done like this 1, this transpose, then this one transpose, x minus 1 x bar transpose, this will be n minus 1 into s. Same formula is we have used here, and we found out S1 for this row, this column and this column, these two column, OD column for process A, ID column for process A. This is S1 you are getting. Using same formula you get S2, you get S3, correct. Then what you require to know? You require to know S pooled. S pooled will be S1 plus S2 plus S3 divided by, because here N1 equal to N2 equal to N3. So, write down like this, N1 equal to N2 equal to N3 equal to N equal to 10. So, my S pooled will be N1 minus 1, that means 10 minus 1 into S1, 10 minus 1 into S2, 10 minus 1 into S3 by N1 is what? 10 plus 10 plus 10 minus 3. So, it is 9 by 27 into S1 plus S2 plus S3. So, 1 by 3 S1 plus S2 plus S3. Now, you see any one of the value, suppose I want to know 1.29 here, how 1.29 is coming? 1.29, the corresponding values in S1 is 1.51, in S2 is 1.43, in S3 is 0.93. So, you sum 1.51 plus 1.43 plus 0.93 divided by 3 will give you this value, that you have calculated earlier also. And then using the formula for M, that big formula, you have calculated M value, that is 1.04, U equal to 0.11, then D equal to 1 minus U into M, that is 0.93. Now, what is your degrees of freedom in this case for D? I say that degrees of freedom is your nu is half p into p plus 1 into L minus 1. So, nu equal to half p into p plus 1 into L minus 1. So, half p equal to 2 into 3 into what? 3 minus 1. So, how that means 3 into 2 equal to 6. So, your degree of freedom for D is 6. Now, chi square 6 with alpha 0.05, that value is 12.59. You will be getting it from chi square table, and then you compare computed D value versus chi square tabulated value. Now, D value is 0.93, which is much less than 12.59. So, we can say we are failed to reject null hypothesis, we are accepting null hypothesis, that means the population covariances are equal. So, we have seen the equality of population covariances are satisfied. Okay. If this is satisfied, then we will go for MANOVA. Now, we will decompose it. So, this decomposition is simple again, it is not that tough. What the slide looks like very difficult one, but it is not like this. What we have seen in ANOVA, we say any observation when you collected XIL, that one is partitioned into. Now, I think again let me see from the population point of view, I say XIL equal to mu plus mu L minus mu plus XIL minus mu L, correct, visible. Now, what is the estimate of mu? That is x bar. What is the estimate of mu L? That you have seen in MANOVA, that is XL bar. Mu L, that is the mean of the L population estimate, is sample mean. So, now we are partitioning the sample observation XIL, which can be written like this: x bar plus XL bar minus x bar plus XIL minus XL bar, that we have seen earlier. So, same thing possible here in MANOVA. This is from ANOVA you have done. Now, from MANOVA you do MANOVA also, we have seen that this vector is mu vector plus mu L minus mu vector plus XIL minus mu L, that is the formulation, and the estimates also will be like this. So, we are writing a vector XIL, which is x bar, that is the sample mean vector, plus XL bar minus x bar plus XIL minus XL bar. Okay. So, you can write very easily, you have seen this one probably earlier, but it is what will happen, this one is P cross 1 equal to, this will also be a P cross 1 plus this difference P cross 1 plus this difference, P variables are there. Okay. This is general partitioning of the sample observation. You do little more manipulation here. What we will do now? We will write like this: XIL minus x bar equal to XL bar minus x bar plus XIL minus XL bar. If you take square, what will happen? Hello? Yes, transpose, because this is a vector form. So, you require to make like this: XIL minus x bar into XIL minus x bar transpose equal to x L bar minus x bar plus x I L minus x L bar into its transpose. Correct. So, our XIL minus x bar is a P cross 1 matrix, transpose will be 1 cross P matrix and the resultant will be P cross P matrix, that is what we want also. Okay. Now, how many dimensions you have considered? One is I, another one is L and other one is J. L equal to 1 to capital L, I equal to 1 to n or n L you write, unequal sample size we will consider here, and j equal to 1 to p. So, we will make sum over these dimensions. First is with I. So, if I make summation I equal to 1 to n L, then this quantity will become x I L minus x bar into x I L minus x bar transpose. This will be, if you multiply this into this into this like this. So, I am multiplying that also, but I am writing first I equal to 1 to n L, then you multiply. So, x L bar minus x bar into x L bar minus x bar transpose. So, this into this plus I can write I equal to 1 to n L x L bar minus x bar into this one x I L minus x L bar transpose. So, first one to second one here plus sum total of I equal to 1 to n L going to the second one x I L minus x L bar into x L bar minus x bar transpose plus sum total I equal to 1 to n L x I L minus x L bar into x I L minus x L bar transpose. See this one, second one x L bar minus x bar into this x I L minus x L bar, and the third one x I L minus x L bar minus x bar. So, this value x L bar minus x bar is independent of I. Similarly, here x L bar minus x bar is independent of I. So, that means I summation 1 to L will be affected here, x I L minus x L bar as well as here. If anyone you take I equal to 1 to n L x L bar is nothing but n x L bar. Again repeat, I am repeating, I equal to 1 to n L x I L is nothing but n x L bar. Means what I mean to say here, I am saying x I L I equal to 1 to n L equal to n x L bar. Now, again summation of I equal to 1 to n L x L bar, this is also n L x L bar. So, this will become, because this is independent of I. So, this quantity becomes 0, similarly this quantity with this becomes 0. So, the two middle terms will be deleted because they are 0. So, then resultant equation will be like this, I equal to 1 to n L x I L minus x bar into x I L minus x bar transpose equal to I equal to 1 to n L x L bar minus x bar x L bar minus x bar transpose plus sum total I equal to 1 to N L x I L minus x I L bar x L bar into x I L minus x L bar transpose, correct. So, this quantity can be further written like this. See here there is no ith term. So, you can straightway write N L into x L bar minus x bar x L bar minus x bar transpose plus this ith term is available here N L x I L minus x L bar and x I L minus x L bar transpose. So, we have taken sum over I. Now, take sum over L. So, L equal to 1 to capital L, then here it will be, here also it will be L equal to 1 to capital L, here it will be L equal to 1 to capital L. So, L equal to 1 to capital L, then here L equal to 1 to capital L. So, do we require the summation over P again? We do not require, because we are doing everything in matrix domain and the vector quantity has taken care of the number of variables. So, we do not require further sum. So, what is this quantity now? Left hand side quantity. This is, if you consider x I L and x bar as a scalar quantity, then this one is a square quantity, and this square quantity from all the observations point of view what you have seen in ANOVA. So, that you have seen in ANOVA this one is SST sum square total, but here it is a vector quantity, and when you are multiplying this vector with its transpose in such a manner it is creating a matrix, not a scalar, creating a matrix of P cross P dimensions. So, we will write this one as, this one will be something like this, P cross P will be, here will be 1 P cross P plus this also will become another P cross P, correct. So, diagonal elements will be the variance part, of diagonal element will be the covariance part, variability and covariance.
First line, third term, that will be summation of, last summation will be with respect to I.
Where here?
The third term, that was second and third, rightmost.
Here.
First line, so this summation should be with respect to I.
I equal to 1 to L, it is given there. I equal to 1 to N L and L equal to 1 to capital L. Okay. So, this one is SSCP total, this is SSCP, what is this? That between population mean vector to the grand mean vector. So, we will write that is between, then this one is error, SSCP error. So, the total covariance matrix, okay, it is not actually the covariance that will be divided by the degrees of freedom. So, we can write that total sum square cross product matrix is divided into two sources of variability, one is the population, other one is the error. So, total sum square cross product is equal to that between sum square cross product plus error sum square cross product. This is the difference from ANOVA, big difference from ANOVA. In ANOVA you will be getting scalar quantity everywhere. Okay. Then what will be the degrees of freedom for this one? It is n minus 1 equal to L minus 1 plus reference n minus L. Same thing what you have done in ANOVA. So, where n equal to what? Sum of L equal to 1 to capital L n L. That is all the observations together. So, in ANOVA we partition SST into SSB and SSE. In MANOVA we partition the sum square cross product matrix of the total to between population and error, correct. So, when you require to calculate SSCPT, SSCPB and SSCPE, it is really difficult. You see that in terms of matrix, transpose, then one sum by over second sum and like this. So, for computation point of view, this one SSCPB is little easier than the other two. So, first you compute SSCPB using this formula, absolutely no problem. SSCPB computation will be like this, L equal to 1 to L n L XL bar minus X bar and XL bar minus X bar transpose, correct. Then for SSCPE there is a formula which is N1 minus 1 S1 plus N2 minus 1 S2 like this NL minus 1 SL. Okay. So, you have seen in pooled covariance case this was divided by degree of freedom, but it is not a covariance one, it is a basically SSCP matrix. So, that degree of freedom is not divided. So, it is S1, S2, SL all you can compute very easily. So, SSCP will be computed, SSCPB also will be computed using formula, then you compute SSCPT, that is SSCPB plus SSCPE. This is the these are the steps basically. First you compute this, then compute this. Okay. So, this is what is our decomposition of covariance matrices, decomposition of I can say instead of covariance matrix, although it is basically the same way the covariance matrix will come ultimately, but it is basically a sum square and cross product matrix you write. I am writing SSCP matrix, that is better. So, SSCP matrix total to these two quantity. Okay. So, I think today we will stop here, and next class I will show you the MANOVA table and then all the tests, how to go for hypothesis testing, then comparison, pairwise comparison and other things. Okay. Thank you very much.